Let's have a look at what else we can do using template point attributes, variables, and functions. This was one question that we received. How do you do lookat? So how do you orient copies towards a given point? And in order to orient a copy, we need to set the copy's template point attribute, which defines its direction, which in the most basic case is the template point's normal. We need to set this normal so that it points to the target point, like so. So what we want in essence is this blue vector here. And in order to get this vector, we need to subtract the point's positions from each other. So what we do to get this vector is we take the target point position, and from this position we subtract the template point position, and this will result in this vector. Let's try it. So these are still my random normals. In this case, what I'd like to do, let's just bypass this point triangle here and drop down a new one. And what I'd like to do immediately is set our p-scale to 0.1. And of course it's p-scale, not p-scale, like this. And let's highlight our normal here, disable the normals so my rubber toys don't look like furry balls, and we can see we have now our copies here. Okay, let's try and orient them towards some point. To do that, we first need to create the point which we like to orient those copies towards. So let's add a point here, check this, add point, highlight it, and with the handle gizmo, let's position it somewhere here. So we can see now we created a point at this coordinate here. Let's wire this template point into the second slot of our point triangle here. And the first thing we'd like to know is, what is this point's position? So what is the position of this single point coming in through my second slot here? When I middle mouse button on the geometry of that single point, I can see I only have this one point here. And highlighting it and heading to the geometry spreadsheet, I can see these are the points attributes here, the position x, y, and z, and the point's number, which is 0 for the first point, which makes sense. So to access these point values, again, there is a function. And what I'd like to get is a vector, and it contains the target point position. Let's call it TGT for target and pos for position. And now let's call this function that is able to read out those values, and it's called point. Point will read point attribute values. And with the cursor in the function name, let's hit F1. We can see we go to this vex page reading attributes, and down here we find point. And we can see the type specifies my data type, which is a vector in my case, and the point function needs those three attributes. It needs the geometry stream on which it should look for points containing a given attribute. It needs the attribute name it should look up, in our case P for position, and the point number, in our case 0, because it's the first point out of that given geometry stream. The first thing we need to specify is the geometry stream. And as so often in programming, we start counting these slots through which different geometry streams come into our wrangle. We start counting these slots by 0. So this is slot 0, slot 1, 2, and 3. So we want to look at the points coming in through slot number 1. Next, we have to specify the attribute name that we'd like to look up, and it's P in our case. So let's create a string called P for the attribute name. And finally, we need to specify the point number on which we would like to look up the P attribute. And in our case, there is only one point coming in through this geostream here, and this point has got the point number 0. Let's highlight this. We can see no errors so far. So I'm now reading in this point's position and writing it into a vector called TGT-pos. Now, when we look at our diagram, what we now need to do is, from this target point position, which we call TGT-pos, let's subtract our template point's position to generate the directional vector. So let's create a vector called dir for direction, and it should be our template points position, which we can access with the @p syntax. Remember, it's just these points coming in through our first slot, and on those I can use my short @ syntax here to access their attributes, in our case P, and I would like to subtract my template point position from my target point position, TGT-pos, like this. So what I do here is I create a new vector called dir for direction, and the value of this vector will be my target point position minus my current template point position. Finally, the last thing I have to do is write this resulting directional vector to our normals. So template point normals, v at n, equals dir for direction, like this. Let's highlight our normal display here, and we can see now we have a bunch of vectors pointing towards our template point. And I think what I did here, let's hit D for display options, and into the guides tab, I scaled my normals down so they don't mess up my viewport that much. So just for display reasons, my normals are scaled down to 1/5 of their original size. Usually by default this is set to 1, and now I can see all those normals pointing straight at my target point here. Let's disable the normal display again and highlight our output here. And we can see now all those rubber toys pointing toward my template point, which, when highlighting my handles here, I can move around. Also, what I notice is when moving around this handle here, my copy to points is quite slow. And that is because I have not checked instancing here, so I'll check pack an instance, which instead of creating geometry for each of my copies here, will just point to an instance in memory, which will make the display and the whole setup faster. So let's try again. And I can see now I can move them around really quickly. One thing I'd like to point out in this point wrangle here, let's highlight it and let's display the normals again. We can see now they can get really long depending on where in our scene the template point is that's pointing to our target position here. And usually the convention for normals and the name normal stems from the fact that a normal vector usually is only 1 unit in length. That means it can point in any given direction, but it'll always have a length of 1. And just to stick to this convention, it's not important for this case, but just to stick to this convention, what we could do is, before we write back our directional vector onto our normal, we could normalize it. And normalizing a vector means scaling it so that it only has a length of 1. And we can do that with the normalize function, like this, and this only takes 1 argument, a vector, which it then scales to a length of 1. Like so. And we can see now those points really close to our target point protrude a bit past this target point because they have now a unit length of 1. And also those points far away from it do not reach it because, of course, they also do have a unit length of 1. In the end, of course, this doesn't really matter to our output because copy to points accepts normals that are also longer or shorter than a unit length. So we are still able to drive this whole thing now and move our target point around. The important point for me here is the point function, which can be used to access point attributes that do not come in through your first input on the point wrangle here. Also, when we go to this help page here, we see Houdini provides a bunch of functions that allow us also to access not only point attributes, but also primitive, detail, or vertex attributes coming in through any of those slots in my point wrangle.